Chris is president engineering and products at Sci5. He leads the product teams on hardware and software, as well as their platform infrastructure. Prior to Sci5, he was at Apple, Tesla, Google, quite an illustrious career creating Clang, as well as the LLVM compiler infrastructure that we just spoke about. So Chris, I'll turn it over to you.
Awesome, thanks, Mike. I'm here to talk about RISC-V vectors and machine learning, a new topic for the conference, I think. So let's start with introducing what RISC-V vectors is all about. RISC-V vectors are a CPU instruction set extension, allowing the CPU to operate on multiple different elements of data at a time. And I think that hopefully it's familiar to many of you. When you compare it to a traditional SIMD instruction set, the basic advantage is that it's variable length. This provides software portability across a wide variety of hardware implementations, which is really key for RISC-V, given the number of different implementations that are available. It also allows interesting software flexibility and code generation opportunities. Now, Sci5 has been driving RISC-V vectors for a number of different years, even to the point where some people joke that the V in RISC-V actually stands for vectors instead of 5. And so we're pretty happy with RISC-V vectors. Now, RISC-V vectors, there's kind of an elephant in the room, which is that it's quite new. And we've announced support for it some time ago, but it's still quite new. And so there isn't a lot of software for it. Now, many of our customers have Neon code. And so one of the things we've built into our compiler technology is a set of compiler features which allow you to just directly compile ARM Neon code directly to RISC-V. And so what this does is this uses the compiler to automatically take Neon intrinsics and re-vectorize them into RISC-V vector code. And this allows our customers to just migrate to RISC-V and RISC-V vectors very confidently because they know they can bring forward their existing software investment. You don't have to start by rewriting all of your code. Now, we've been using this to bring up a large number of pretty big software packages on RISC-V vectors, which is really great. But of course, many of our customers really want AI. And so they bring us, they're very happy that they can get going and get started quickly with AI solutions. But it turns out the AI on the edge is really kind of unfortunate for a number of reasons. Now, if you take a look at this problem, there's a couple of different ingredients to it. One is that a traditional CPU just doesn't have the amount of horsepower you need to be able to do AI inference effectively. So the standard solution is to take a traditional CPU, get a big hard-coded accelerator block, and there's many of those available, glue them together, go to town, and claim you have a solution. And this used to work. And this worked with the last generation of machine learning models, which were pretty simple. They're mostly just matrix multiplications, convolutions, element-wise operations that were quite simple. But it doesn't work as well for modern algorithms because AI moves very quickly. The other challenge with these solutions is that while you may get infinite customizability, it turns out the tools don't always work very well. They're a little bit fragile. Bringing up a new model is very difficult. Often you have to talk with the FAEs of the company that you're working with. And so you end up with a lot of duct tape and baling wire holding the whole thing together. And this makes it very difficult to move quickly. And particularly if you want to bring in a new model from research, it can be very challenging. So of course, we think that a really good solution is to bring together the advantages that RISC-V has with the advantages that AI accelerators have and pull these together into a new solution. So today, I'm happy to announce a new initiative called Sci5 Intelligence that we're using to pull together all of our AI technologies and solutions into one umbrella direction. Now at Sci5, we're taking a software-first approach to AI. And the reason for this is that AI is not a means, it's not an end on itself. it's a means to an end to build high-quality products that users interact with, right? And so those users interact with applications. Those applications need neural networks. Those neural networks need acceleration. And so if you work backwards from the software to the hardware, you can build more purpose-built, better hardware solutions that are useful for accelerating the workloads that matter today. Now, of course, we have a variety of high-performance hardware solutions, and we'll be launching one today. But we want Sci5 Intelligence to be the one-stop shop that provides scalable solutions for ML, particularly for inference. Now, I mentioned before that AI is moving very quickly, and I just want to double-click on that really quickly. Where before you would have traditional, simple, dense neural networks, today's neural networks are moving very quickly. So if you look at language models, for example, many of them have moved to the transformer architecture. This includes machine learning models like BERT, if you're familiar with that. these things have a softmax stuck right in the middle of the attention layer. And so if your accelerator can't accelerate softmax, what ends up happening is you have to constantly ping pong data between the accelerator and the other compute parts of your stack, which basically eliminates the entire purpose of accelerating in the first place. Similarly, if you look at recommendation models, you need sort to do top K. There's people doing reinforcement learning, which requires integrated support for CPU compute. People are doing fine tuning of neural network models on the edge, and this requires a certain amount of retraining, and this means dynamic shapes often. And so what we want to provide is a solution where you can build a hardware technology solution and have it still be relevant by the time your chip tapes out. Because if you build something with a last generation architecture and you can't deploy the neural networks that people want when your product ships, you're kind of stuck. So today I'm happy to announce the SiFive Intelligence X280. And so the X280 is a unique combination of AI acceleration, RISC-V vectors, and our silicon-proven RISC-V core. And it starts with the extensions. And so we've added support for the standard data types that you'd want to use with AI, including bfloat16. We've added custom accelerator solutions that give you high performance. We've built on top of RISC-V vectors. And so our solution has 512-bit architected registers. And this allows you to get up to 512 bits of data out a cycle. And of course, they're variable length. Now, we build on a really awesome core, the U7. This is silicon proven. Our customers love it and use it in a wide variety of applications. We're very happy with this. But we've combined it with a high performance memory subsystem so that you can feed the machine. And I'll show you later, the performance of this thing is pretty incredible. So this is not a, in the distant future kind of product. This is available to lead customers now. And I'm really excited that just yesterday, in fact, we announced a partnership with Tenstorrent where they're using the X280 in their upcoming high performance data center accelerator for a wide variety of use cases. And they're very excited about the flexibility that this product provides as well as the performance. So coming back to software, one of the distinguishing features of this is that we provide full support for TensorFlow Lite. I think this is a first for RISC-V, but it's also very unusual for accelerators in general. TensorFlow Lite supports there's over 100 models on TF Hub, and it supports a wide variety of other use cases. This is the standard way of deploying inference solutions from TensorFlow. And this is built on top of a full technology stack of software, but also the X280 and its extensions. Now, why do these extensions matter? Well, first of all, they provide data type support for things like bfloat16, but it's also about performance. And there's a couple of different ways we'll look at this. The first is a micro benchmark, because micro benchmarks are great, right? And so if you look at int8 matmul, this is the key operation that much of inference ends up building around. You'll see that while RISC-V vectors provide a lot of compute you can fit a lot of int8 elements in a 512-bit vector, but matrix multiplication is a spatial operation, not a vector operation. And so with dedicated acceleration capability, you can actually get a 12x speed up over and above vectors themselves. We think this is a pretty big deal. Now, this is just a micro benchmark, and this is one kernel, for example, and so you may wonder if this actually helps in general. If you take a look at a more realistic example, we'll use MobileNet as our example because it's one of the most widely benchmarked models that exist. You'll see that RISC-V vectors provide a huge speed up over scalar code. In our case, about a 24x speed up over scalar code. And the SiFive Intelligence extensions together provide another 4x speed up on top of RISC-V vectors. End to end, this provides almost 100x speed up for MobileNet. And this is huge. This suddenly makes, it kind of changes the game with RISC-V vectors, changes the game with RISC-V, and we think it will move AI in a new way. Now, of course, these products can be tiled in many different ways, and you can build very large-scale solutions as well as a single core, depending on your use case and your workload. So to wrap it all up, I want to reemphasize the SiFive Intelligence X280. We think this is a great product that will support a wide variety of different use cases for our customers. This is also the first step for SiFive in terms of AI. And we're investing a lot in both software and in hardware, and taking that software first approach, which you'll continue to hear about in the forthcoming year. These extensions are great for performance and capability, but the key thing I want you to take away is that building with SiFive Intelligence allows you to run the models that are just being dreamed up in research today. And that's a huge capability because you don't want to build a product that ends up not being able to run the models that are contemporary with the products that your customers want to build. Now, we think that RISC-V is the obvious choice for machine learning. First of all, we think that the ML world, because it's still very early, is hyper fragmented. We think that consolidating it together onto a standard platform is very valuable. We think the modular nature of RISC-V is the perfect fit for AI problems. And we think the SiFive Intelligence X280 is really a great product for many different use cases. So if you're interested to learn more, I'm happy to answer questions. And there's a lot to talk about in the future. Thank you.
Okay, thank you, Chris. That was quick. So you can go ahead and turn off your screen sharing, and we'll get to some questions. So with the introduction of what you call the SiFive Intelligence Extensions, so are you saying that you're introducing some things, features to your CPU cores that are proprietary, or is this going to be part of the RISC-V open specification?
Yeah, these are currently proprietary extensions. We do work very closely with the RISC-V Standards Committee, and we're pushing both RISC-V vectors and many other things forward, but these are currently proprietary.
Okay, all right. And there's no plan then, yeah? I mean, you're gonna use this for differentiation then?
I mean, we have no announced plans of what we're doing with them right now.
Right, but it's a change in strategy from supporting the open source common ISA to adding your own custom extensions now.
SiFive has added custom extensions for some time. Now we're not shy about that. I mean, our customers have full access to our software toolchain and things like this, so it's pretty well known what we're doing. Okay. But we also don't want to be limited to moving at committee speed. So so there's a balance to be traded off there.
Got it. Okay.
Also, the thing I would say is that traditional CPU software and AI software are very different. When you're talking about AI software, you're not necessarily looking for portability across architectures the way you would with traditional vector code. The reason for that is that you have to care a lot more about memory hierarchy, about a lot of other performance implications than just the vector length. And so the code that you end up generating often ends up being tailored to even the CPU implementation, not just the not just like all RISC-V vectors everywhere. And
sure.
the difference is often something like a 10x performance difference if you're not using your memory effectively.
Right. Well, so it sounds like you're positioning your CPU with these extensions as an alternative to the more custom optimized accelerators. Do you really see it as an either or what we've seen from other IP vendors, for example, is a combination of a CPU with an accelerator where the CPU or the DSP can handle some of the other programmable layers. What's your position on that? You're actually trying to do the entire neural network on a CPU?
Well, so I think that if you zoom out and look at the space of hardware solutions here, I actually just gave a talk about this on Monday, an hour-long tech talk nerding out about this if you're curious. Really, what you end up seeing is you end up seeing tiled solutions often, right? And they're tiled because of wire delay getting between different parts of the chip. Within each tile, then you have a control processor and an accelerator block. And the ratio of control processor to accelerator varies, right? And so you'll see some things, for example, the TPU V1 from Google was a tiny little control processor that was mostly a sequencer combined with a big matrix multiplier, right? Mm-hmm. Other times you'll see different points in the space. A general CPU is the furthest other extreme where you don't have any parallel acceleration, a scalar CPU. Right? And so there's many different points in the space. And what we see with RISC-V vectors is that vector register file is a really nice, very close SRAM that's very useful for optimizing and executing a wide variety of workloads. And so we do put a significant amount of area into the AI acceleration, but using the RISC-V instruction set as a sequencer and control processor works very well. And I think that when you compare it to it's hard to generalize across the entire AI industry because there's many different approaches, but many folks will design their own like a VLIW control processor, or they'll make a little more than a state machine to control their accelerators and things like this. The problem with that is you don't have software. And so the building kernels to run on these things is actually very complicated, requires a lot of performance analysis, and having RISC-V with the entire RISC-V software ecosystem, so you have a debugger and you have simulators and all this kind of stuff out of the box, is really powerful.
Well, yeah, I was going to ask you about the memory because that's a key for any accelerator design. But then still, compared to a data flow architecture, do you see that approach with the register file as being of sufficient efficiency to really support high performance networks or low power networks?
Right. So the X280 has both the register file, which is the L0 cache, right? That's the tightly coupled memory. It also has a private L2 cache for every core, and these cores then get tiled out and can share an L3. And there's multiple different memory hierarchies that you can set up. Okay. And so the register file, or the vector engine in general, typically runs from the L2. And so we have a pretty sizable L2 cache that then fits the majority of the model that you're running inference with.
Yeah. Okay, I've got lots of questions. I've got questions coming in from the audience. Yeah, I think this is similar to the question I had. But so do you add your own instructions when you're accelerating TensorFlow Lite? You're using some of your custom extensions to do that?
Yeah, yeah, absolutely, right. And so the key thing that we hear from our customers is that they don't want to, they don't want a some assembly required solution all the time, right? They want to be able to get other projects done rather than starting by rewriting an entire software stack. And so this is how the reason we look at SiFive Intelligence is a combination of hardware and software solutions that work well together. Because if you can walk up to the stack, have things just work, and then tune as much as you want or customize or do, there's lots of flexibility in the stack, of course, but if you can get running quickly, then you can decide how much time to put into optimizing any one different part of your problem.
Got it, okay. I think you said that for the 280, it's available now to lead customers. What's the status of general release and development tools and such?
So general release is out in a couple of months. So I don't know if we've announced, but we're shipping for early Q3. You can use it today on FPGAs, for example.
Okay, but that's just for lead customers right now.
Yeah, yeah. Okay. And we're very happy to work with people to become lead customers. That's no problem.
So since it's proprietary, then access to the documentation will be on a customer by customer basis?
I don't know if we've decided how we're going to handle the documentation. All of our existing documentation is public, and we've even recently made it so it's reshareable and rehostable. Okay.
And then is the 280 targeted for the edge data center? What's your scaling target?
Right now, we're targeting it for the edge primarily. Now, so what I say is I would explain it as being used for edge because that is the simplest thing we provide all the software solution for today. However, I'll caveat that with advanced customers like TensorTorrent are already deploying it and building products for the data center. And so the fact that it's a tiled architecture is really powerful because it means you can build very scalable solutions depending on how much area you want to put down. And so we're focused primarily on making it really turnkey for the edge, but for more advanced customers who are more AI literate and AI focused, right? They can do many different interesting products around this.
You showed what you called some of the micro benchmarks and some kernels. Made a brief mention of, I think, MobileNet. Any other well-known neural networks that you've been able to demonstrate this on?
Yeah, we can run the full gamut of TF Lite models. And TF Lite supports all the standard industry models that you'd expect.
Okay, all right.
Yeah.
See some more of the audience questions. Grant, we know that you used to work at Cadence. Question from Grant Martin said that you seem to be implying that TensorFlow Lite on 280 is the first, but Cadence Synopsys and CVAL support TensorFlow Lite. I think you said specifically first on RISC-V.
Yeah, well, it's very hard to say the first of anything because that includes lots of qualifiers. I don't know if somebody in academia has played with RISC-V on TF Lite. Things I would be careful to point out is that TF Lite is very different than TF Micro. TF Micro doesn't run many of the models that exist today. It's a different technology stack, effectively, with a different set of tools around it. but yeah, I don't think, I mean, TF Lite supports a number of different architectures, and so I'm not claiming that we're the first to support TF Lite for sure.
Right. Uh, yeah, I was question. The next question is on the data types you're supporting. I thought it was interesting that you're also talking about supporting floating point. Do you see that? I mean, given that you're targeting edge inference applications, nice to have the flexibility there, but you're not really going to see that on an edge inference device, right?
Well, actually, it depends. It depends a lot on the use case. So often with quantization, so I'm a big fan of quantization. Of course, if you can get if you can get down to int8, then you get much better memory and performance out of the chip. However, FLT32 is really important. Often the first layer you don't want to quantize, and when you do that, you lose a significant amount of accuracy from the model. Now that really depends on the model, and so that's true of mostly image models. And so if you're doing computer vision tasks, you don't generally want to quantize that first layer. But doing mixed precision training, and there's many different approaches to this. Now, FLT32 is also important because on the edge, people do want to do a little bit of training sometimes, and it's very it's not unusual to want to be able to fine tune a model that you've trained and shipped with your application, but then tune it on the edge. And this is used, I think, it's more by the advanced folks than the standard let's run MobileNet kind of use case. But this is a rising importance.
Well, for on-device retraining, we had presentations on that earlier in the week.
Mm-hmm. Yeah, and so again, our approach here is to provide a very optimized for the cases that are the high performance, the thing that makes it an AI accelerator, but make it general enough that if you want something new, if somebody comes out with a new layer in research, you're not dead, right? Or you're not falling back to scalars or something where you're off a huge cliff that makes it unusable.
But that's all configurable. You don't have to put in that overhead of floating point
right.
if you want it.
Right, of course.
Yeah.
And then this also builds on SiFive's strengths in terms of configurability of cores and many other things.
Yeah. So can you support less than int8? Are you looking at lower precision?
Well, so I mean, it depends on what you mean by that. so Boolean networks are supported with and or and things like this, which doesn't require any special hardware support. We don't have support for int4 because we don't think it's widely utilized at this point, but it's something that we're willing to look at for future generations.
Right, but does your software then allow your customers to make those trade-offs?
So we don't support...
It sounds like you're inherently supporting mixed precision. Then there's always a trade-off on how much precision per layer is adequate.
Right. And we support the standard TensorFlow-Lite tools. And,
right.
I mean, again, this is one of the things where AI software tools are often a bit fragile, and often bespoke AI software tools are even more so. And so we think that using standard tools is very valuable because these are battle tested by the team at Google, by the world. There's a lot of miles on these tools, and so we don't think that it's necessary to make. We don't think that just ignoring those tools is the right thing to do. We think that embracing the ecosystem around that is valuable for the industry.
Yeah. Right. Okay. It's a question on whether you see the X280 competing with FPGA solutions, which of course are configurable, instead of programming the software instruction level like in your CPU.
Sure. Well, I mean, I think that the X280 has it depends on which FPGA you're talking about, right? Because FPGAs these days have hard blocks, and FPGAs these days have hard RISC-V cores in them. FPGAs also have hard AI accelerators in them, right? And so depending on exactly which one you're talking about, it's all just a ratio kind of a question. But if you're talking about a classic FPGA, you'll find the X280 is a much more power efficient solution. It's much more tuned for AI. It doesn't have the ability to run like general hardware compute things in parallel like an FPGA does. And so it's really tuned for ML. And so if you're trying to do non-ML things, then an FPGA may be a great solution. But if you're trying to do ML AI, then X280 is a good fit.
Got it. You mentioned that your software can translate the ARM Neon code. But ARM is also moving to SVE. SVE2 now has been announced. with RMV9. Are you going to provide a translator for that as well?
We don't have any committed plans to do that, but I think it's a logical next step. The reason we haven't done it is mostly because we don't have customers who have asked for it yet. There's not a lot of SVE code that exists in the world yet. And so I think the SVE and RISC-V vectors are kind of the same state of penetration in the software market. The day people want that, I think that we'll happily do that, and the technology we provide is definitely extensible with that. I think it will be even easier than providing RISC-V vector or Neon compatibility.
Got it. Okay. Let's see, more questions coming in. Since your objective is to support new and upcoming machine learning models, a lot of the ML community is using PyTorch. Are you planning to support PyTorch?
It's definitely on our radar. I'm sure we will. We don't have a committed date for that. But yeah, we're very well aware of PyTorch and we're fans. Don't have a committed date.
Got it. Okay. Then there's a question on whether you have anything that's similar to the x86 MMX instructions.
Do you mean, does it share state with the floating point stack? Well, we don't have a floating point stack. Again, it depends on what you mean by MMX. MMX was a 64-bit wide integer vector SIMD instruction set. It's fairly obsolete now, so I'm not exactly sure what the question is.
Okay, person who asked that can go ahead and follow up with you later on in the breakout session, I suppose.
Sure.
You mentioned high performance memory interface. Specifically, how wide, what kind of memory bandwidth are you talking about?
So we have a 256-bit data path to memory right now.
Okay.
Yep, and that talks to Axie4. I think there's a block diagram in the slides that gives you kind of a high-level view of how the DPaths work.
Got it. But when we talk about high performance, we've seen in some of the other accelerators, much wider memory access ports, dual store, those kind of features available?
Yeah, we definitely support memory concurrency. We definitely have our path to the L2 is very high bandwidth, and so that's an optimized path. We do try to run L2 resonant workloads.
Yeah.
So that's the optimized case. Again, right now we're focused on the edge solution, and many of our customers want to put our products into a kind of traditional mobile or other form factor, and so it's integrating, a few X280s, 1 to 4 kinds of span is the typical kind of use case right now.
Got it. Okay. So with these vector extensions, then I think some of the work in the RISC-V working groups has been the different groups working on AI and another group working on DSP. Are you looking at supporting DSP workloads with these extensions as well?
Do you mean the P extensions?
Well, yeah, right. For signal processing. I mean, architecturally it looks similar, but I just wonder if you're adding anything to your ISA to support signal processing rather than have two separate cores. What we've seen, like in the previous Cadence presentation, for example, is it's a DSP core connected to an accelerator. And that when you're processing a lot of these, especially the edge applications, you're doing sensor processing. And so an integrated solution makes sense.
Yeah, so it depends on the specific question. So the major difference between RISC-V V extension, the vector extension, and the P extension is that the V extension adds a big vector register file. And the P extension overlays on the integer general purpose registers. And so if you're putting hardware down for the vector registers, it's much better to use that because you'll get way better performance out of doing that versus trying to shove things into a 64-bit register, right? And so we think signal processing on RISC-V vectors is a very good thing to do. And so we are definitely interested in the space, but I don't think that P is a great solution unless you don't want the V extension.
Right, but if you wanted to do sensor processing on the 280, is that a good solution?
Yeah, you can do FFTs, you can do standard algorithms on this. This is one of the great things about the RISC-V vector, the RVV platform, is you look at the standardized platform and ecosystem.
Okay, great. Well, thanks again for making the announcement and sharing some of that here this morning. And we'll see you in the breakout sessions later on.
Yeah, thank you. I'm happy to meet you.